Welcome to Math 150, Section 2, Lecture 5, 2021. Today we will be doing a little bit on spherical and polar coordinates, a little bit on cylindrical, not so much because it's really a nice mix of polar and spherical. We'll talk a little bit about level sets, and we'll talk a lot about one of the extra credit bonus problems, because this is an outstanding problem to use as a springboard for how should you think about problems, how should you attack problems. And so the question was, you're given 1, 2, n squared in an n by n matrix, find the determinant. So whenever you have a problem like this, what should your first thought be to try? What's step one? You want to gather some data. So what would be a good value then to try first? Easiest value then to try? 1. 1. So when n equals 1, we have the matrix that's just 1. Right? The determinant is 1. This might be a little bit too simple to really give us anything. So building on our remarkable success, we now try to what a shot, right? When n equals 2, we now have 1, 2, 3, 4. And the determinant is 1 times 4 minus 2 times 3. What does that equal? -2. Ah! Is this enough to detect the pattern? No. 1, -2, what comes next? 3, yes, and what comes after that? 1, -2, 3, -4. Beautiful. Oh, wait a minute. Maybe it's 2 to the 0, 2 to the first. Maybe it's 1, -2, 4, -8. There's just too many things that could happen right now. So let's look at n equals 3. 1, 2, 3, 4, 5, 6, 7, 8, 9. Cultural extra credit for today. What movie has a famous password of 1, 2, 3, 4, 5, which is the same as someone's luggage? 1, 2, 1, 4, 7, 2, 5, 8. And we said the way we calculate the determinant, we multiply down like this, and those are all the pluses. We multiply up like this, those are all the minuses. And when the dust settles, the determinant is 0. Now we haven't really talked about how to do higher determinants in this class. There is expansion by minors. You may have seen this in algebra 2. You might have some vague memory of Cramer's rule to solve systems of equations by calculating determinants of minors. And we can make a little table. And the determinant of our invariant is 1, 2, 3, 4, 5, 6, 7. 1, -2. And I will just give you the next couple of values. So based on this, what would you now conjecture? The rest of the bazoo. Do you feel reasonably confident about this conjecture? Yeah, a lot better than we did about the 1, -2, 3 or the 1, -2, 4. Yeah, we now have a lot of data and it seems to be fitting a pattern. Now, 0 means something very interesting. Geometrically, what does the determinant of a 2 by 2 matrix represent?
The area of the cross product of two vectors, the parallelogram.
The area of the parallelogram. And in fact, if you take the cross product of the two vectors, the length of that is the area. So it has a nice geometric meaning. If we have 3 dimensions, what does the determinant of 3 vectors represent? Good, so instead of area, we would say body. It's the generalized area. Now, what does it mean If we have a 2 by 2 determinant that's 0, what would that mean?
They're parallel.
They're parallel. So what kind of parallelogram does it generate? A line. What would it mean if in 3 dimensions we had 3 vectors and the volume was 0?
It's also a line.
Not a line.
Or a
Plane. Here, a plane has 0 volume in 3 space. And so what this is telling us is that one of the vectors is a combination of the others. It's not generating a full space. So if we look at 1, 2, 3, 4, 5, 6, 7, 8, 9, somehow one of the rows must be a combination of the other 2. Can you think of any way to get the middle row from the first and the third? I know that that's the easiest one to do, that's why I'm focusing on that one. How could you get, what do you see, what do you notice 1, 4, 7, what do you notice?
Add 3.
Add 3. What about 2, 5, 8? 3, 6, 9. How could I view 1 and 7 and 4? How can I get them? How can I get 4 from 1 and 7? What can I do?
Plus or minus 3.
But I've got 1 and 7. How can you get 4 from 1 and 7? What operation can you do to 1 and 7 and get 4? You can average them. So 4 is the average of 1 and 7. Is 5 the average of 2 and 8? Yeah. So we basically get row 2 is 1/2 row 1 plus 1/2 row 3. So row 2 is just a combination of rows 1 and rows 3. And what's nice is by observing this, we don't need to know the big formulas for determinants. We just need to know that the m by n determinant is the volume. And the volume is 0 if we don't have enough dimensions, if it doesn't span out, if one vector is a combination of others. If I did 1, 2, 3, 4, 5, 6, 7, 8, how would I get from 1 to 5? I would add 4. I would be going from 2 to 1, 2, 3, 4, 5, 6. I would be adding 4 again. So here, I'm in the 3 by 3 case, I add 3. In the 4 by 4 case, I add 4. What do you get in the n by n case?
You add n.
You add n. So this should hopefully be enough of a hint now to come up with a complete proof. That the second row is always the average of the first and the third. Well, if we think about this, why did we get 0 in 1 and 2 dimensions? Why are we getting such a different answer? Well, let's see. If I want to say one row is the average of the other, of 2 others, how many rows do I need? At least 3. If I only have 1 and 2 rows, I can't really talk about one row being the average of 2 others. I don't have 2 others. So it makes sense that this is something that's going to kick in only when the dimension gets larger. And this is just one of many examples of how things in math will change as your dimension goes up. In one variable calculus, it is really not that exciting to talk about finding a limit. You have 2 paths. I go left, I go right. That's it. I think in the video it talked about the squiggles. You've got to be able to deal with calculus coming in along paths like that. That's a lot more freedom. It is a much stronger condition to be differentiable in several variables than it is to be differentiable in one variable, because you have so many more paths you can take. So I love this problem. You don't need the advanced theory of determinants. You just need to think, what does the determinant mean? And you need to be able to get some information gleaned out of it. So the more determinants you can calculate, the more confidence you're going to have in the results. always start with the simplest case and build up from that. Sometimes the simple cases are so simple, they don't really show you what's going on, and it takes a while for the limiting behavior to kick in. Later in the semester, if people are interested, there's a wonderful chess problem where the limiting behavior is very different than what you expect. And I generalized that with William student and another colleague here last year. All right, any questions about this? All right, so again, gather data. The more data you have, the more you can try to conjecture and see what's happening. Okay, so the next part is to talk about spherical coordinates. Unfortunately, depending on who you talk to, you can get different definitions of spherical coordinates. This means you must very carefully look at whatever book you are using and be careful and aware which notation are they using. The physicists and the mathematicians often have slightly different notation as to what do you call the angle coming down from the z-axis. I learned first in my physics classes, and so for me, I always have to consciously think when I'm teaching in the math department to use the math notation. Which notation is better? I think the math notation actually is better, but I am just hardwired now to the physics notation. I will risk saying this. One of the things I truly wish my wife had never done is introduce me to some of her cousins with the diminutive versions of their names from when they were kids. Because I have to fight not to call them that now. She just said, this is my cousin Dan, this is my cousin Rob. It would have been much easier for me to just process that as their default name. But it gets very hard to overcome notation that you use. You really want to think about what are we naming things and why. For spherical coordinates, so everybody should have some spheres on. Yes? Okay? So you can test your spherical coordinates later. So we will call that a sphere. What do you think spherical coordinates generalize? That you've seen before. So spherical coordinates generalize circular or polar. Sometimes called circular or polar coordinates. We have a circle. We have a point r theta. So x is r cosine theta. Y is r sine theta. So r is the square root of x squared plus y squared, and theta is the arctangent or the tangent inverse of y over x. So the idea is if I give you something in one coordinate system, I should be able to convert it to the other. And hopefully, if I give you an x and a y, there's a unique r and theta. I give you an r and theta, there's a unique x and y. This is almost true. It turns out there's one point where, unfortunately, I don't have a unique point that it's sent to. Anybody know that one troublesome point?
0.
0. 0, 0 in Cartesian. So theta is completely free. Because once r is 0, it doesn't matter what theta is. It's still going to be at the origin. So there is a slight issue with the change of variables at that one point. It's not a big deal. And things still work out, but you do have to at least be aware of it. Whenever you see a function that depends only on x squared plus y squared, you should be thinking polar coordinates. Or maybe cylindrical coordinates if you have cylindrical symmetry. A lot of things only depend on your distance. Polar coordinates are not surprisingly ideal for things in the plane. Spherical coordinates are ideal for spherical. Does anybody know any object in the world that depends only on the distance from something? only depends on the distance. Any forces that depend only on distance. Gravity. So gravity is any two objects, at least according to Newton, attract each other, and the force is proportional to 1 over the distance squared. It doesn't depend on the angle, it doesn't depend on phi. It only depends on the distance squared. So that would be an ideal situation to use spherical coordinates. And so what we want to do is we want to figure out what to do from rho, theta, and phi. And here, we'll often have r goes from 0 to capital R, and theta will go from 0 to 1. So you tell me how far out I go, and I just swing around. Well, I check if I swing around this way. All right, so now let's look at what's going on in spherical. I start off with the z-axis, and phi is how much I come down the z-axis. Here's the z-axis, here's the x and y, and here is the angle phi. So rho will go from 0 to the radius. And then I have to figure out where do theta and phi go from. Well, if I start at the North Pole, how far does phi have to go? I could go all the way around, which would be 2 pi radians. But remember, once I go down a certain amount, I then have my theta, and I can start spinning around. And so imagine I go down 3 radians to here. And now, if theta goes from 0 to pi, I actually travel a circle that's parallel to and above the equator. Well, I've hit every point. Yes, and I'll hit every point once and only once. If phi went all the way around and continued, and then I spun from 0 to 2 pi, I would hit points multiple times. So we tend to like theta to go from 0 to 2 pi to spin all the way around. How far will phi go? Phi will go from 0 to pi. And we always do things in radians. What's the derivative of sine of x? Cosine of x, only if you work in radians. If you work in degrees, there's a conversion factor of 2 pi over 360. When we think about this, what's going on? Well, this is a circle. What kind of variables do you want to use for a circle? So what variables do you want to use for a circle? For coordinate systems. Polar. So here, I have my radius, and I have theta for how much I spin along. So if I look at that circle, it's at height c. It has some radius r and some angle theta. So this point on the circle, the x-coordinate would just be r cosine theta. The y-coordinate would be r sine theta. And then we would have z. Now you can see why mathematicians like to have phi as the angle coming down from the z-axis. Because if phi is the angle coming down from the z-axis, then that means we can use theta for the angle in the circle parallel to the xy plane. That's why we use rho for the radius, because that way we can use little r for the radius of the smaller circle. So the whole point is to make it easier to use the polar coordinates. So if you think about what's going on now, I come down from the z-axis phi radians. So this over here, that r, is going to be my radius. So I need to figure out what is r. if we wrote that point as r cosine theta, r sine theta, z, this height over here is just going to be my z. So I need to figure out how do I express r and z in terms of rho and phi. Any thoughts? How can we express r in terms of rho and phi?
Rho sine phi.
Rho sine phi. So the sine of phi is r over rho. The sine of the angle is opposite over hypotenuse. So that gives us r equals rho sine phi. And similarly, cosine phi is going to be z over rho, and that gives us z is rho cosine phi. So now we know exactly how to use polar coordinates for this problem. We know what little r is, we know what little z is. And we now get x is rho sine phi cosine theta. Y is rho sine phi sine theta. And z is rho cosine theta. So this gives us x, y, and z in terms of rho, theta, and phi. So you tell me rho, theta, and phi that uniquely determines an x, y, z. If I give you an x, y, z that almost uniquely determines an a rho, theta, phi. What's the one point that doesn't determine uniquely a rho, theta, phi? 0. The origin, again, is the one point that doesn't uniquely determine. What is x squared plus y squared plus z squared? What would that equal? I'm sorry? Not the radius cubed. The radius to what power? Think of units. If x, y, and z are in meters, what's the unit of rho? So radians is essentially a unitless dimension. So sines and cosines, they're just numbers. If x is in meters, what unit must rho be? Meters. So this has to equal rho to what power? Has to be rho squared. Now, it could also depend on some terrible function of theta and phi. But it has to look like rho squared because that's the only way we're going to get something that has units of length squared. If you look at what's going on, if you look at x squared, y squared, z squared, each one of them is going to have a rho squared. So it's clear that x squared plus y squared plus z squared has to be rho squared times something. I encourage you to do the algebra yourself. I will just do it quickly on the board. Sine squared phi, cosine squared theta, sine squared phi, sine squared theta. Oh, I've got a cosine squared theta plus sine squared theta. What's cosine squared theta plus sine squared theta? 1. So when I square them and add these vanished, I get rho squared sine squared phi plus rho squared cosine squared phi. Or what's sine squared phi plus cosine squared phi? Still 1. And so if you square and add, you will get x squared plus y squared plus z squared is rho squared. Do you ever need to do this calculation again? No. Once you've done it once, you have the result. So we know x squared plus y squared plus z squared is rho squared. And another easier way to see that is, here's my origin, here's my point x, y, z, and I have it on a sphere. So rho is representing the distance from the center to my point. So I have the vector v is the vector x, y, z. How do you calculate the length of a vector? So we're letting rho be its length, but if I tell you the components are x, y, and z, how do you find the length of a vector whose components are x, y, and z? Pythagoras. And this is actually generalized Pythagoras. And what could be better than Pythagoras on the plane? Pythagoras in higher dimensions. So you get x squared plus y squared plus z squared. So this is another way to check and make sure everything is consistent. Okay. So when we're looking at what's going on, if I can use a function e to the negative x squared plus y squared plus z squared, what would that be in spherical coordinates? Give you e to the negative x squared plus y squared plus z squared, what would that be in spherical coordinates? E to the negative rho squared. And the hope is that for some problems, it's going to be easier to look at things in spherical coordinates than in polar. Than in Cartesian. Okay. This is now the 5th class of the semester. By now, I think it's been established that my artwork sucks. What shapes do you think I can draw? Don't all show confidence in the instructor. Okay, triangle. Yes. What else do you think I can draw? A square. Can I do a little bit better than a square? Well, that looks like a big. What's a little bit better than a square? A little bit more general. Rectangle. The square is a very special rectangle. I think I can actually make the size. Well, let me put it the other way. I don't think I can make the size the same way. I think it's much easier for me to draw something like that. So I can do rectangles without too much trouble. Let's go back to polar coordinates. In polar coordinates, a circle, I said that is x squared plus y squared is less equal to big R squared. That would be a circle of radius capital R. How would you write the equation for a circle of radius capital R in polar coordinates? How would you represent a circle of radius, how about the whole filled in circle? All the points inside a circle of radius capital R. Good, so that's what it will look like. So how would you write in terms of little r and little theta? Well, that's how you would plot it. We'll do that in a moment. So say, here's how I wrote the equation involving little x, little y, and capital R. How would I write the equation involving little r, theta, and capital R?
Wait, what's the difference between big R and little r?
So I'm talking, little r is going from 0 to r. Little r tells me how far I've gone. If I want a circle of radius capital R, maybe capital R is 4. And then little r will run from 0 to 4. Maybe capital R is 9, and little r will run from 0 to 9. So I want little r to have some freedom to move. So how would I translate this to polar coordinates?
You could do.
Somebody. Okay, so what would I get? So how does x squared plus y squared less equal to capital R squared? How does that get converted in polar? What does that look like? So you get little r squared is less equal to big R squared, which we can simplify to R is less equal to big R. And if you look at this, if you try to plot this, if I put theta down here, and I put R over here, what I get is a rectangle, which was remarked earlier. So the whole point of polar coordinates is it takes a circle and it replaces a circle with a rectangle. Which do you think is a nicer shape to work with? Rectangle. Is it hard to calculate the area of a rectangle? This is essentially how we define length times width. The area of a circle is a much more interesting challenge. It can be done. We are eventually going to do multiple integration. When we do multiple integration here, I can think of it as theta goes from 0 to pi, little r goes from 0 to 4. Two very nice integrations to do. If I were to carry this value, if I fix the value of y, oh my god, x is going to run from negative square root of 1 minus y squared to square root of 1 minus y squared, and then y is going to go from negative 1 to 1. The region of integration is going to involve the surface, the curve. So we'll talk about how to do it. But it's much easier to work on rectangles because then the two bounds are completely independent of each other. Rectangles are very nice shapes to work with. Yes.
So if you're finding the area of your little rectangle, wouldn't it be, 2 pi r? But isn't that circumference?
Good. So the area of this rectangle is 2 pi r. That is not the same as the area of the circle. Because what you're saying is each unit of area here corresponds to exactly the same amount here. There's no conversion. So I know we have at least one person who has at least one family member not in the United States. I think you mentioned Netherlands. So the Netherlands is on the euro. So there is a conversion factor between dollars and euros. Is the conversion factor common? I'm sorry, constant. Good, it can change day by day. So if I actually had a plot of the conversion factor, it will fluctuate over time. Does the conversion factor depend on how much you have to convert?
Even a little bit.
Yes.
Like, if you convert a lot of it, then the value of one will go up and the other will go down.
Well, I mean, the banks might give you a deal if you're converting a tremendous amount. I have some Canadian money on me. Okay, we're not that far from the Canadian border. Does it matter? This is such a small amount of money. I'm probably going to get the same exchange rate to any of this. It's going to be a constant exchange rate. Imagine how things would be if the more you have, the better rate they give. You think of a reason why a bank might be willing to do that. Why might a bank be willing to give you a better exchange rate? Yeah. Yeah, so if the bank is making a certain amount per transaction, or a certain amount, the more the bank does, the more money it makes, the less it needs to make on each little bit. When you're buying things, you get a discount if you buy in bulk. Yes, if you're willing to buy 100,000 units, let's talk, I'll cut you a deal. And if you're going to give you that much business, it can often be worthwhile. So it's a great question why it's not exactly 2 pi r. And the reason is each little bit of area here does not correspond, that the amount changes depending on the radius. The further out you are, it looks like it maps the same amount over here, but a small square here with a large radius is going to map to a larger segment than a small. If you think about this little bit at the top, that would give me say the stand outside. Now if I take a little bit on the bottom, and so you can see that even though they are the same over here, they're not the same here. But there's going to be an exchange rate between the two. And that's going to be a huge part of the course when we do multi-variable integration, is how do we figure out how to convert? I'd much rather integrate over a rectangle, but I'm going to have to pay the conversion cost. And if the conversion cost depends on where you integrate, then you have to keep track of where you are. It's much nicer if things are constant. But most of the conversion factors that are interesting will not be constant. Yeah.
So when you write your units, like of the rectangle part, not like of the circle part, would you have to keep the radians, like write that down even though it's units?
Well, yeah, you want to be very careful. So how many of you have seen RD theta? We will talk about this when we get to integration, that you really need to be careful about theta. You should always have theta associated with a radius. And this is one of the other reasons why we like to work in radians, because then the length of the arc is related to the length of the angle that is created. And everything comes out very nicely like that. One brief application. Does anybody remember the formula for the volume of the sphere, radius r? Sorry, 4/3. Yeah. The volume of the sphere radius r is 4/3 pi r squared. Does anybody remember the surface area? Excellent. What about the area of a circle of radius r? Pi r squared. And the perimeter two pi r. And everything has the right dimensions when we do it like this, which is good. Do you notice anything to go from area to perimeter? There is divided by 12. There's more than one way. However, it's the derivative. How about here? How do we get from here to here? It's also the derivative. This is not a coincidence. If you think about what's going on, if I take a sphere of radius r, and I increase the radius by delta r, I can ask, how does the volume change? So the change in volume is approximately the change in the radius times the surface area. And again, I'm waving my hand and being complete. Delta V, delta R is approximately the surface area at R. Also, in the limit, the derivative of the volume with respect to the radius should be the surface. What's nice about this is there's a lot of math you need to memorize. If you remember one of them, you can get the other. I know the volume, I can get the surface. As an aside, there is a great argument in Feynman's lectures on physics as to why Newtonian gravity should be 1/r². So imagine everything in the universe pulls on everything else. And we'll say that the effect of the force on you is related to how many pulls you get. And so I have some point source and it's sending out yankage. And the more yankage I feel, the stronger I'm pulled in. As I go out further and further and further, the amount of yankage it sends out is constant. If I take a small little segment, it's going to feel more pulled closer than further away. If you go far out, how is the surface area of the sphere increasing? The surface area goes up like r². So the yankage should go down like 1/r², so that their product is constant. So that their product of the sphere of radius r will be independent. So I'm sending out the same amount of net force. This is just meant to be a heuristic as to why gravity might be 1/r². And again, whenever you can tell a story, it is worth doing so. All right, so the last thing I wanted to talk about briefly is level sets. So level sets typically causes the most problems of all the material in this part of the semester. There's essentially no calculus in what we're doing is algebra, and it's just trying to find out which points that evaluated to the same level. So I like to think of level sets as telling me which points are at the same height above sea level, or something like that. So the level set of f of height c are all inputs sent to c. Right. So imagine you could have some mountains. There's 0, there's 1,000, there's 2,000, there's 3,000, there's 4,000. And so I want to find all points that are at a certain level. How many points are at level 4,000? 4,000 feet above sea level. Yeah, so if c equals 4,000, level set is the answer. What if c equals negative 1,000? You could be including them. If you look at this classroom, what's a good level set to look at? There'll be lots of things in this classroom of that height.
What's the best?
The desk. So the desk, we have an incredibly self-conscious team that works night and day to make sure all the desks are at the same level. Wherever you sit, it will be the same experience. Same for the team. So if you look at whatever this height is, that'd be a great example. In the first class, somebody said 3 feet. Actually, you keep a tape measure on me. If you go 3 feet from the ground, this will be somewhere between your belly and your head. And so there will be a lot of level sets at 3 feet. Ceiling is another good one. You have something over here. You go all the way up until you hit the ceiling. So lights would be another one. If I choose the value of 1,000, I would have a bunch of different things. So all the points into here, and then the points in here, and then the points in here would all be in my level. So the hardest part is just trying to find which inputs evaluate the speed. So you're basically looking for F inverse of C, looking for all the points that are central to C. So a good function to look at is sine squared, is sine x plus y squared. Sine x squared plus y. Let's say f of x, y is the sine of x squared plus y. What can you tell me about the values of sine squared? I mean, the values of sine. Where does the values of sine live? Perhaps sine of x squared plus y squared. How large could sine of something be? How small could it? Okay, so this is going to be between -1 and 1. So if I'm trying to look at the level set, and I look at C, here's 1, here's -1. It's empty. So level set is empty if the absolute value of C is greater than 1. What's the first value of C where I have a chance of seeing something? 1 and -1. So I could basically go coming to either way. So let's try to find all x and y such that sine of x squared plus y squared equals 1. We have a function that depends only on x squared plus y squared. What should we use to study it? So you should have a Pavlovian response. I have the sine of x squared plus y squared. What should you be thinking? what would be a good coordinate system? Circle, polar, right? Circle or polar, either one is fine. Does this depend on where we are in the XY plane? Yes, but only weakly. All that matters is our distance from the origin. This is the same as the sine of r squared equals 1. Right? What angle has a sine of 1? Pi over 2. Anything else? Not 3 pi over 2. 3 pi over 2 is a sine of negative.
Oh,
So we'll use that in a moment. So what else has a sine of 1? So it's 90 or pi over 2. You go all the way around, and it'll be 5 pi over 2. And then 9 pi over 2. We keep adding 2 pi. So r is equal to the square root of pi half, or the square root of 5 pi over 2. So the level sets is just going to be simple. If I gave you -1 rather than 1, then we would use your 3 pi over 2. And it would be 3 pi over 2, and we would be 9. It would be 3 pi over 2 plus 2 pi, which would be 7 pi over 2. Then 11 pi over 2. If I give you any other c between -1 and 1, it's going to be very similar. If I give you sine of r squared equals c, let's say we take c equals u2 over 2. So what angle has a sine of u2 over 2? Pi over 4. You would say r squared is pi over 4. Anything else have any other angle have a sine of root 2 over 2? 3 pi over 4. And then you can add 2 pi to this. So we would have 9 pi over 4, 11 pi over 4. So for anything else, we actually get 2 values of the angle that way. At 1 and -1, we only get 1 value. So we're going to just get a bunch of circles. So again, there is no calculus here. This is just algebra. And that's why I think it causes so much trouble. But to find the level set, you're just asking which inputs go to that level.
is it ever going to be in 3 dimensions?
Yep. And so let's do a 3-dimensional one right now. Let's do f of x, y, z equals x. And I want to find the level. Do you think any c will work? If I give you any c, you can find x, y, and z. We want to find x, y, and z such that f of x, y, z equals c. So let's try to solve this. What would x be? What would y be? What would z be? So my function is f of x, y, z equals c. What should x equal? What should y equal? What should z?
C.
X equals c. What about y?
B.
Y is true. And z is true. So the level set is just x equals c. What kind of object is x equals c? Not a line, it's a plane. You have 2 free parameters. Y and z are completely free. Let's write it in a more enlightening manner. 1 times x plus 0 times y plus 0 times z equals c. This is now in the form of normal started with x, y, z equals normal started without point. If I write it like this, is it now clear that this is a replaceable point? So I deliberately chose a tricky sum. I deliberately chose one where two of the coefficients are zero. So if you think about this, maybe x represents our we have some object here. Maybe x is going to be height. And what this might be saying is that all that really matters is your height. So if you're thinking about maybe the ocean, maybe what matters in certain areas is just how high are you above sea level, above the ocean depth maybe. Or if I have some kind of compound, maybe some of the stuff is settling because it has different density. And the density might only depend on how high up I am. So this would be a nice function which only depends on one of the three components. This is a function that's going to be constant on plane. Okay, so I think we're basically at the point where we've done enough so we can do the first exam. So I'll be sending you some information about that later. I will probably do a class that is not a new material class, just to give extra time to study things and ask questions, maybe a programming class. Because you get a little bit of time to do stuff like that. All right.